Hello everyone. This is just a short video to show you how can we use the MVSP to load VSP data and display VSP data and to process them and to interpret them. So for the data loading, firstly I have to go to File, so I can import different kind of data formats. So I will load here the SIGY, which I have in the folder. So I will import it, and then I will go to the data where I have the VSP, and then I will click the display button in order to check my data if it is loaded properly. And here I can see the data, and I can change the gain to uh, to display it and to check the different types of signals and noise which are available in my data in order to design my um, processing workflow. So then I will just save my data and I will give it name. So I will give it Z00. It's good to be sequential in the ordering and in the naming of the data file. So then I will refresh the data list, and then it will come here, and then I will be able to display the data. I will click on wiggle display, and here I can increase the gain or the scale so that it will be visible in a better way. So if I increase the gain, for example, 5 or more, I can put as much as I want. So I see here that I have some noise, and I will see some kind of downgoing waves and upgoing waves, and some random noise and some coherent noise, and some noise is arriving before the first breaks. So this is what I will try to process, and I will try to eliminate. So firstly, I will try to use the different tools which are available here in the different menus. So here we have menu for visualization, and we have different types of tools for flattening and for comparison between different data set, and for static correction, for frequency analysis. We have also tools of processing, so we can do several types of processing, different types of techniques: AGC, energy balancing, and BP or bandpass filtering, predictive deconvolution, winner deconvolution, medium filtering, FK, SVD, KLF, and trim statics, true amplitude recovery, top muting, and bottom muting. We have here the interpretation. We can have the composite plot. In the composite plot, we can integrate the VSP or the processed VSP data with the logs. We can also display the velocities which can extract from the VSP data from the T and the D, time and depth. We can also do the modeling or the VSP modeling, starting by velocity modeling and then shot modeling, and here we can use the ray tracing. And lastly, we can export our VSP data in SIGY format or SU format or MATLAB format. So let's start do the processing. So now, firstly, as we have seen in the beginning, the data, it looks weak in amplitude, and so I have to increase the gain in order to make it visible. So what I will do, I will try to increase the energy and to balance it so that the data will be clear and the energy will be balanced, because we are supposing that the energy is coming from the same source, so it has to be balanced. So if I will choose a time window, and I can have different tests, and I can see the data before and after the energy balancing. So here we see data before and after balancing. So we see the amplitude here is strong and it gets weaker and weaker, but here as I applied the energy balancing or equalization or amplitude equalization, it looks like the amplitude all are the same because they are all coming from the same source. So here the energy is balanced. So I will save the data after the balancing, and I will call it Z01 energy balancing. So it's done now. And I will refresh it and I will be able to display it now. So it's here now. I can also apply the AGC in the processing. So the AGC will increase the gain of the data so that it will be better in terms of display. So this is the data before and after. If I can test different windows, so here when I use short window, the AGC effect will be much strong. So I will keep 1 here, it means 1 second. So I will save it and I will make it 02 AGC so that I will be able to track my data. So it's here now. So I can display it. Now I see my data after the AGC. So now what I can do, I can increase the gain. So I see here that I have downgoing waves, I have upgoing waves, and I have some noise, some coherent noise, and I have some random noise. So I will try to eliminate all that noise and to improve the data and separate the downgoing from the upgoing waves. So now firstly, the most important thing in the VSP is to pick the first brick, and I have to have good quality of picking. Otherwise, I will be having problem in the the next tasks. So here I will increase the scale in order to be able to see the first arrivals. Then I will zoom it. So now I will pick the first brick. I will choose here pick event. So I will be picking the first arrivals. And once I will finish my picking, I will hit and click on enter. So my event will come here. If I'm not happy with it, I will pick it again. I can improve it because it's very crucial, and having a good picking will allow me to avoid many problems in the processing and will provide me with very good quality at the end. So I will accept this one. Then I will save it at the header. I will choose the field number 15 so that all the peaks will be saved in the header number 15 or in the field number 15, and it will be time peaks. So then I will save it, and this will be Z01 3 FB means first brick. Okay, so then done. So now what I can do, I will test my first brick are there or not. So I will do top muting in order to kill all the noise which comes before my first bricks, because it's a noise. And you remember that I have saved mm, my peaks in the header word number 15. So then display. So this is the data before, and this one is after. So here I see that the noise which comes before the first peak is muted. Good. So I will save it here. Z04 first brick top mute. Then so now I will try to do the flattening. I will do the downgoing flattening. And the downgoing flattening, I will also use the peaks which I have already peaked, and I have top muted. And here I will choose the time at which I want to do my first brick peaking. So I can check. For example, it is, I will try to flatten my data according to the first event here. So I will make it example 0.2, and I will see. So this is the data after the flattening. So here the VSP data are already flattened. I can test different times, but here, for example, I will choose 0.2, 0, because I can improve it. 0, Z0, now I'm in 5, 0.5, down, flat, okay, and quit. So now this is my data after the flattening. So now the next step, I will try to clean the data and to filter out and to suppress the upgoing waves, because here I have the upgoing waves and the downgoing waves. So we see them here, and they have many noise. So we have flattened only the downgoing waves. So now what we can do, we can apply the medium filter. It's very easy to apply. You can use also the FK or the SVD, but here I will use the medium filter because it's very safe and very easy. So I will choose the length of the filter to be 11, and I will choose my data, and then I will apply. I can test different lengths and see. So we see here that the data now is cleaned. You can use also the FK for the same purpose. Okay, so now I will just try to extract the upgoing waves. by subtraction. So if I have the flattened, I have the flattened downgoing waves, and I have the downgoing waves which I have just cleaned and thrown away, and I have thrown away the upgoing waves. So if I subtract one from the other, I will have the upgoing waves in addition to some noise, coherent noise, which, so these are the upgoing waves. So you see them here. And this one is a noise. And this one, this strong one, it could be also a noise. So we will try to eliminate them. Try to eliminate the noise and keep only the signal. So these are the downgoing waves. And these, they are, and these, they are all kind of noise. Z 07 up. So now what I will do, I will refresh, and here now I have my upgoing waves. So next, what I will do, I will try to flatten my upgoing waves, upgoing flattening. So I will choose downgoing, which I have extracted, and my peaks are again in the header word number 15. So I will ask him to flatten my data at 0.2, and I will see. We'll test 0.1. Okay, so this is the data before and after the flattening of the upgoing waves. You see here that the upgoing waves, they are flattened now. So now we see that the upgoing waves are also noisier because they contain too much noise, coherent and random noise. So we will clean them as we have done in the downgoing. So first we have to save them. I'll give them a name. So then I will refresh, and then what I will do, I will apply the medium filter again in order to remove the noise which is present in the upgoing waves. So I will choose 11, and I can, for example, use another odd number. And this is the data after the medium filter, and this one is the data before. So we see that the coherent noise is eliminated, and it's not present anymore. This and this, and these are the upgoing waves. But we still here have some noise coming from the suppression of the noise which is here. So some residual noise, we can clean it with FK, for example. We can apply, for example, the FK. this is the FK filter, so we can load our data, select, then we can choose the Fmax, which we have here. We can test in order to get the FK domain. So this is the data in the FK domain. I can increase the scale here to make my data visible. So 5 is too much, so I will keep only 2. So here I can reduce, I can change the minimum and the maximum. I can make it so I see that all my events are in this trend. They are following the y-axis, and all the noise is residing and is staying away. So then what I will do, I will define a polygon where I can expect my signal. So this is my FK polygon. So then I will ask the program to pass or to reject. So I will pass all what is in between or inside the polygon. So when I press FK filtering, this will be the data after the FK. And I see here that the noise which has been here is suppressed, and I see very continuous events here. So I can even zoom in the events, and I see them here without the noise which is here. So now I can save my data. I can save even the FK polygon, but I don't need. So I will save only the my filtered data set. So this one will be Z FK, and then I will close the window. So now I can display it in my main window, and I can increase the scale. It's too much. So this one. So now I can do a couple of things. For example, I can compare my data set. So in terms of frequency and in terms of amplitude. So here, for example, I can bring my Z00, and here I can bring my downgoing, and here I can bring my final upgoing waves. So here I can increase the gain. And here also, so I will keep the same. And here, so I see here the data in raw mode. So when it was only raw data, so without cleaning noise, and here after cleaning, after flattening, and here after after the separation of the downgoing and the upgoing, and here I have only the upgoing waves. So I can also I can see also the frequency of my data. I can display them. For example, I can bring my FK data here. You can take my first trace, time from 1 to let's say 2.5, and this one will calculate the spectrum for me. So this is the data from 1 to 2.5, and this one is for the entire data set. So I can see here I can increase the scale, for example. So this is my data set. So I can use this one for the analysis of the data frequency content. So lastly, I can do the corridor muting and um, stacking. So I can pick the outside corridor. So I will bring my data, which I want to do the corridor muting. So I will increase the gain to see the data clearly. And here I can choose the corridor width and how many trees I will leave at the end. For example, I can leave 5. And here I will try to see the corridor. So I can increase the width. So if I increase the width in this way, I will have I'm supposing that I don't have multiples here. So this area where I have corridor stack, it will be free of multiples. So then what I will do, I will save my peaks. I will choose the field number 16 to save my peaks, because the previous one I used 16. So I will save it. And lastly, I will do the outside corridor. I will mute the data in the inner part or the outer part of the the upgoing waves. So here I will put the number 16 where I have put my peaks, and then this will give me, this will be my upgoing. So I suppose that here I don't have multiples, and as I can see here, so these are primaries and this one are multiples, so they are not available here. We cannot see them here and here and here, but if we can come here, we see the multiples which come immediately below the origins. So this will produce for me the Z11 outside corridor. So for the inside corridor stack, I have two options. I can just subtract the outside corridor stack from the data. So I will have the inside corridor stack, or I can do the same thing. I can do the inside corridor stack or corridor mute, and I will choose my data after the cleaning. So I will choose um, the field number 16 or the header word number 16 where I have saved my peaks. Then I will have my inside corridor. So, and here I will name it Z12 inside. Now, lastly, I will try to stack. I will stack my inside and outside corridor. I will average them. And here I will choose how many traces I want to display. So it means replicate or duplicate. So these are my traces after the summation. I will do the same thing for the outside. So these are the outside and these are the inside. You can even stack the cleaned upgoing dataset so that I will be able to compare all the data which I have. Then I can refresh to see all my dataset. And lastly, what I can do, I um, can use the view in order to see the multiple plots. So and see all this one is the inside and this one is the full stack. So I can zoom in and zoom out, and I can increase the gain if I want, and I can compare and do my analysis and my interpretation. Lastly, I will just show you an example of the use of the SVD, for example. So we can use the SVD, singular value decomposition, which is also a very good filter to remove and to separate downgoing and upgoing. So let's have an example. I will select my data set, which is noisy. So I see the noise here, and here I will choose the number of values which or component which will keep only the downgoing and remove the noise. So I can stop, for example, at 4 and see. So here I see that the data is almost removed and only the upgoing, downgoing waves are kept. So I can save also the data and use it. I can also show you where I can apply, for example, the static correction and calculate the time to depth. This one should be done, of course, after the first peak. So the KB elevation is at 643. I will do the static corrections. Then I will calculate the velocity. So I see here the time versus depth, because now I have corrected the depth, because the time is counted from the source, which is on the ground, and we're using vibro size, which is on the surface. But usually the depth is recorded from the KB, so there is some time and some depth correction which has to be done in order to make them coming from the same level and same reference, and then to put them in a way that we can correlate and we can associate one with the other after the correction, because the time which is coming actually from the vibro size is not vertical, so we have to make one of them to be vertical so that we can have good time to depth um, coordinates. Then if we have the time and depth, then we can calculate interval velocity and average velocity as we see here, and we can display the geometry of the acquisition. So the source is here and we are shooting. So, and the time which we are recording is actually the time which is the wave is taking from the source here up to the receivers. These are the receivers here in the borehole. But the depth is actually measured from the KB, which is here. So there is some correction which has to be done in order to be able to correlate or to associate time with depth. So then I can save the, I can save my coordinates and depth for further uses later on. I can also use velocity modeling. Velocity modeling, I can use, for example, this model to create a velocity model. So, for example, I will use 100 distance or width model, and I can use 1000 meter depth, and the seal size will be, for example, 10 meter. Velocities I can use, for example, 1500. I can use three velocities to 5000 and 3500. And for example, I can use also another velocity. So I have four layers. So then I have to give the depths. So the first one will be, for example, at 150. The second will be at, let's say, 700, 370. And then we'll have another one at, let's say, 670. And lastly, we'll have 1000, which is the total depth. And then we can create our model. This will be our model. So then we can save it in the program so that we can use it for the modeling. This will be our V model. Can refresh and we can find it here. This model, it can be used for shot modeling or for ray tracing. For shot modeling, we can create VSP shots. So this will be my VSP shot, which has been modeled using the velocity model which I have created. Then I can do the processing which I have done for the real data set in a similar way. I can clean the coherent noise and the random noise and these artifacts which are coming from the modeling. I can apply the AGC, I can apply the muting. And here I see in the synthetic data that I don't have any noise or energy which is arriving before the first breaks. So that's all. Thank you for watching.